Okay, so we shall continue. We have one thing left. We have a way to calculate the last mode, iterations. Then we have a way to calculate the first mode with iterations after we apply a shift. Now, in order to calculate other modes, that is not the last or the first, we need to use something called deflation. Okay? In order to explain deflection, I have to first talk about what are left side eigenvectors. So the right side eigenvector is this, right? That is, if we multiply d times phi is phi times lambda, because the eigenvector is on the right. Now, assume that you consider the problem of the transpose of the matrix. The transpose of the matrix has other eigenvalues, but it has the same the transpose of the matrix has the same eigenvalues, although it has different eigenvectors. Why are the eigenvalues the same? Because transposing a matrix does not change the characteristic polynomial. You can confirm that by just looking at it yourself, transposing it and computing the determinant polynomial, and you'll see that transposing the matrix makes no difference. Therefore, the eigenvalues, which are the roots of the characteristic polynomial, must be the same. Now, if you take this eigenvalue problem and you take the transpose, then you see that you get this. And therefore, that's why we call these eigenvectors, that is, the eigenvectors of the transpose of a matrix are called the left side eigenvectors, because they work such that if you multiply them as a row on the left side, you get the row multiplied times the eigenvalue. Okay? Now, once we know that there are left side eigenvectors, okay, no big deal, they are just computed as the right side of the transpose. It is interesting to see what is the relationship between the left side and the right side. So for that purpose, we can do something like this. Imagine that you have the matrix D and the first eigenvector on the right. That would give you this, right? Now imagine that you take now the transpose and you consider, actually I shouldn't do 1, I should say I. So we consider the ith right side eigenvector, and let's say we consider the jth left side, which is the right side of the transpose. So then we have this times lambda j, right? And you should see where I'm going, right? So I take now the transpose of this and I get d, wait a minute, I get phi j transpose times d, right? Phi j transpose times d equals to phi j transpose times lambda j, right? That's what we said was the left side eigenvectors. Now we can copy this one here, and we have d times phi I is equal to phi I times lambda I. Now let's pre-multiply this expression by phi j transpose. So we would have here phi j transpose and here phi j transpose, right? And then let's post-multiply this equation by phi I. So then we have phi I here, and since lambda j is a scalar, I can just move it, and so I have phi I lambda j, right? Now you can see, this is very similar to what we did in class last time. These two things are the same, therefore subtracting we get 0, and on the right side we have phi j transpose times phi I times lambda I minus lambda j. Therefore, if lambda I is not equal to lambda j, then the right side and the left side eigenvectors are orthonormal. That is, phi j transpose times phi I is 0 if j is not equal to I. Okay? Now, we can, of course, we can normalize such that the left side, so we can say that the left side j transpose times the right side j is of course not equal to 0. That's only 0 when these two things are different. But we can normalize such that phi j transpose times phi j is 1. Okay, so that's a convenient normalization between the left side and the right side eigenvectors. All right? Okie doke. So now we know that not only are there right side eigenvectors, which repeat themselves times lambda, but there are left side eigenvectors, which repeats themselves times lambda. Right? Like that. Right side, left side. And we know that the right side times the left side is 0, except when they have the same index, and they can be normalized to 1 if we want to. Now we are all set to introduce the method of deflation. And the idea is this. Say you have lambda n and lambda 1. You want lambda 2 now. Okay, so you look at the problem d shifted, right? D shifted times let's see, how do I say this clearly? D shifted times x0 is equal to x1. D shifted times x1 is equal to x2, etc., right? And we proved that since lambda 1 is the largest, this converges to lambda 1. Now what we are going to do is we are going to say one way that we can ensure that this procedure converges not to the largest eigenvalue but to one before the largest is if we can make the coefficient of the largest equal to 0. I wish I had kept, but I don't know that I have here. So it's something like this. Remember that XL was equal to phi 1 times lambda 1 to the L plus times B1 plus phi 2 times lambda 2 to the L times B2 plus, and it went like that, right? Until phi n lambda n to the L times B n. One way that we can assure that this thing does not get overwhelmed by this term is by making Bn equal to 0. So if Bn is equal to 0, then the largest term is this one, right? So the method of deflation, okay, the method of deflation consists in a trick, which I will just show you the math quickly, or the procedure. It consists in a trick in which we ensure that our x0 is such that our b last is 0, and so we get the next one. Then once we get this one, then we make sure that these two are 0 and we get the next, and so on. So we continuously deflect and we get as many modes as we want starting from the end. Now, if we apply it to the d-shifted, we get lambda 1, we get lambda 2, lambda 3. So in this case we had lambda 1. Because we are working with the shifted, we would get then lambda 2, then lambda 3, and so on. If we apply it to the d with no shift, then we would have lambda n, and then lambda n minus 1, lambda n minus 2, and so on. Okay? Now, let me just give you, to conclude, because I've taken too much time, let me just give you the deflation formula. So, if I want to get rid of the first mode, it can be shown that the deflation formula is just simply the identity minus phi, the left one, transpose times the first one, and that's the matrix. So we replace ds by ds times n1, and the procedure converges to lambda 2. Okay? Now, if we want to get lambda 3, we can use n that gets rid of 1 and 2. That would be the identity minus the left one transpose times the right one minus the left 2 transpose times the phi 2. And in this approach, we now ds by ds times n1, 2, we get lambda 3. Okay? So these ends are the deflection matrix, and I guess you see the generic pattern, right? You want to deflect the first mode, you need this. You want to deflect the first and the second, you need this. You want to deflect the next first and the third, you need the next one, and so on, right? Now, to conclude, I need to give you a practical way to get the left side eigenvectors, okay? How to get the left side. You might say, but you already told us. Because what? Because I said that the left side eigenvectors are simply the right side of the transpose, right? So you could say, if I want to get phi 1, I could try to solve ds transpose, right? Because then I can say that that times phi 1 is phi 1 times lambda 1. But no need. Okay? There is no need. Why there is no need? Because it can be shown that for the case, actually I shouldn't have done shifted. It doesn't really matter, right? Without shift, just The shift is irrelevant. The shift is for the procedure. But if I solve d transpose times phi1 times lambda 1, that would be the left, right? So, but there is no need. It can be shown that for the problem where d is equal to m to the minus 1k, then the left side eigenvectors are simply equal to the mass matrix times the right side. I was about to prove it right now for you here, but I would leave you that as an exercise. Try to see if you can prove it. I will show it in class. It's very easy, right? You just say, let me look at the right side, let me look at the left side. Well, actually, I shouldn't say it's very easy. It's easy if you know what you're doing, but you've seen it before, but maybe I lost perspective. Anyway, it turns out that the left side eigenvectors are equal to the right side multiplied times phi j. And to calculate the deflection matrices, the matrices to deflect the modes, it is necessary to normalize such that phi j transpose times phi j is 1. Okay? Which you can always do. That is, imagine that you have just calculated your phi1. Imagine that you just calculated your phi1, right? And it was ABC. And now you want to calculate your left side phi1. So what do? Well, you take your mass matrix, you multiply it times your phi1, and you get your first shot at phi1, right? But you can then say phi1 transpose times phi1, and you get 7, for example. Then, of course, that's not normalized, right? So what is the phi1 that you want? You want phi1 equals, phi1 normalized would be your previous phi1 divided by 7, right? Now it's normalized. Okay? So, all right. So this, I took time to give you an example in MATLAB. I mean, to post, it's already in Blackboard, that has every one of these steps with commentary and clearly outlined in an example. So with this lecture that you've seen here, plus that code, not as a code to use it for other things, I made it for a particular example, but you can track it and you should be able to get any doubt that you may still have at this moment clarified. I will, of course, prepare a little homework so that you have to try it yourself, but you can at this time, or at any time of course, simply propose for yourself any square matrix from m to the minus 1k, you know, generate an m and a k, and then you can just try to calculate eigenvalues and eigenvectors using the power method, and you can always check them easily, right? Because you can ask MATLAB what are the eigenvalues and the eigenvectors. And in the MATLAB example, I've actually done that. I've shown what the solution is and compared it to the MATLAB solution. Okay, so I'll see you guys, when is it? Tomorrow, right?
Yeah.
Okay, so long.